of the most iconic scenes in science fiction is in Star Wars: The Empire Strikes Back, where Han, Leia, Chewbacca, and C-3PO are hiding inside an asteroid cavern from the Empire, only to realize it's not a cavern, it's the throat of a giant space monster, the Exogorth or space slug. Star Wars isn't noted for its scientific accuracy, and that scene is also notorious for implying asteroid belts are dense minefields where a pilot needs to dodge rocks constantly to avoid death. But they're not alone in using giant space monsters, and I'm not so sure that giant organisms in space is scientifically unrealistic, or even on planets like the immense sandworms of Frank Herbert's Dune. So I thought we might contemplate giant space monsters in today's Nebula exclusive for January of 2024. Canonically, our first episode for this year. Now there is a noticeable difference between the various cases we'll consider, as each has different problems with the possible biology, and we can break them into 4 loose categories for discussion today. First, we have our space slugs or space whales living in actual space, which is our main focus. Then we have your more classic kaiju, giant monsters on planets like the sandworms of Dune or Godzilla. The key differences there are air and gravity. Life is hard without air, and big life is hard with gravity. So we can imagine 2 major in-between cases: large critters living in low-gravity oceans and large critters floating in low-density atmospheres. We can and will also contemplate both artificial planets like the hydroshell and artificial life forms engineered to be immense, to circumvent evolutionary hurdles. Now, we cover the basics of life potentially evolving or living in the vacuum of space in our episodes on void ecology and space whales, and indeed we have episodes for the special case of a conscious planet or star too, but let's talk about the space slug from Empire Strikes Back. There's a lot of problems with that scene that emphasizes the issue with biology here. For one thing, they walk out in what appears to be decently normal gravity, which is bizarre in an asteroid, as even giants like Ceres only have 3% of Earth normal gravity, and most asteroids wouldn't even have 1,000th that gravity. It also shouldn't be pointing sideways in one direction, since that cavern is vertical, and there's no reason for an atmosphere. They aren't wearing spacesuits, just breather masks, and that place is moist and humid. Now, nothing in physics currently outright forbids some weird technology that might let you generate artificial gravity, possibly in some photoelectric equivalent, absorbing photons and emitting gravitons. We'll call it photogravitic, and we can't always imagine some path to it occurring in nature, much as photosynthesis does. We could imagine a big critter using gravity to attract prey and having a moist oasis there as part of the lure. We could also just write that scene off as artistic license, and instead imagine large critters evolved there because it was easier to get in space, no gravity crunching you down, and that it does not breathe. It just uses sunlight to run itself and process metals and rock into its organic or quasi-organic existence. As we discussed on our episode on low-gravity planets, it's reasonably plausible a colder and more volcanic planet might have taller mountains that rose up to above the atmosphere, and where you might see life slowly adapt its way to live all the way up the mountain, especially if it was constantly simmering with lava and venting gases. From there, an eruption might carry microorganisms used to near vacuum into space, and we could easily imagine this smaller planet was actually a larger moon like Jupiter's moon Io, tidally racked and volcanic, and was around a planet like Saturn that has those big and ancient ring systems. Indeed, such eruptions might feed those rings. That's merely one example of how life could start in conditions akin to Earth and make its way into the void of space, and we have others we looked at in that void ecology episode or in our episode on panspermia that contemplates life simply originating in space all on its own. However it gets there, this is one occasion where bigger is better, because however its biology works, it likely needs to spend a lot of energy keeping warm, and a big insulated shell helps with that, and helps with keeping your insides inside. Odds are good that you have internal chemistry with gases and fluids. I could even imagine a big space monster having natural thermocouples that extended throughout their body to generate energy for them. Indeed, such veins of metal also might be their equivalent to either an exoskeleton or even an endoskeleton, and metal bones certainly help with size. If you've got an energy flux, you can support life, and that means anywhere you've got stars or even planets by themselves. I could easily imagine finding natural Dyson swarm equivalents where some space critters formed a complex ecology around their sun in space by migrating out from a planetary ring into asteroids and smaller moons, and maybe even disassembling them into some lower density and wider cross-section conceptual equivalent to coral reefs or tree canopies. Such being the case, these space trees might be many kilometers in size, and the animal equivalents potentially just as big, or even bigger, coming by to graze on them or hunt whatever did. Locomotion is trickier. There are some big space amoeba they encounter in Star Trek Voyager that propel themselves along using flagellar movement with little whip-like oars, and that works fine in a fluid but not in a vacuum. Moving in space is either going to require some natural sail using sunlight or magnetics or ionized particles, or it's going to involve crunching up rock or ice to make a vapor you can expel. So long as we are dealing with rocks with an escape velocity of less than 100 meters per second, which is very nearly every asteroid or comet in existence, then we could imagine a creature with a large bladder filled with gas while metabolizing ice or rock. And if it's a big critter, then this gas bladder or orifice it emitted through might be home to smaller ecosystems. So in this regard, I could imagine getting swallowed by a giant space whale like Jonah and finding an oasis inside it, and we might even imagine some civilization arising that lived inside miles-wide space monsters and learned to steer these whales around. I cannot imagine any of these space monsters posing an actual threat to a spaceship, unless they weren't intelligent technology users, which makes you a threat be you big or small. We see a lot of them in Star Trek too, and they played it straight in the Next Generation episode Galaxy's Child, where a big space critter attacks the ship as they're examining it, and they unintentionally kill it while trying to drive it off with their phasers on minimum power. Today's episode originally aired on Nebula, and every month we have an exciting new full-length episode that airs exclusively on Nebula, and this month's Nebula exclusive, Fermi Paradox Air, explores how atmospheric conditions could act as filters for life in the universe and what sort of strange alien creatures may evolve under alien skies. But Nebula is home to tons of other awesome content too, like Faithless, a Sojourn story, a feature-length audio drama exclusive to Nebula. Set in the Sojourn universe, it follows Castrian Vadric's quest to reunite with his beloved. Faithless continues to expand the ever-growing Sojourn setting with exciting and entrancing stories in the best traditions of space opera. This episode is available now on Nebula, the creator-owned streaming platform where every SFIA episode airs early and ad-free, and where you'll find exclusive content like the Fermi Paradox, Air, Faithless, or many other monthly Nebula exclusives and content from many other creators. Use my code IsaacArthur to get 40% off an annual plan at go.nebula.tv/IsaacArthur. That's less than $3 a month, with lifetime memberships and gift cards also available. By joining Nebula, you'll be directly supporting this show. And now, back to giant space monsters. To transition into giant space monsters on other planets, science fiction loves to show us big dinosaurs facing off against heavily armed humans, but the reality is this wouldn't tend to end well for the dinosaur. Obviously, a firearm made for killing humans is not sufficient, though sheer weight of fire from an automatic weapon might get one and they're hard to miss, especially if we're using armor-piercing rounds. But even a medium-light machine gun like the M250 cal, sported by most military vehicles such as Humvees, would chew one up, and something heavier like the M242 25mm machine gun on the Bradley IFV or Mark 19 would obliterate even such a titanic critter. Something stronger like the main gun on a battle tank or A-10 Warthog would amount to overkill, probably even against Godzilla. Even the biggest dinosaurs were only about 80 tons, not even 10 times the mass of an elephant, and less than the biggest modern whales, which can get to maybe 200 tons. This doesn't mean they aren't dangerous, of course. A Kodiak bear is usually under a ton, and it can kill a human, even a skilled and armed hunter, and the hippopotamus is quite dangerous and kills hundreds of people a year. So yes, some colonist on a new planet could get themselves plastered by a local space monster even without exceeding dinosaur scale. They just aren't a civilization scale threat. If you know they exist and have prep time, you will handle them, because you are smart and have technology, and they do not. Unless they do, of course, they might have very large brains, though it is a reminder that humans don't have the most massive brains, and that sheer brain size doesn't imply much intelligence. But it does not counter-indicate it either. Big critters might be more likely to be smart. They might have a brain 100 times as big as ours, and even if they can only spare 1% of that for higher functions, well, that's pretty smart. Indeed, they might have a networked brain with nodes throughout their body to handle signal delays, and other backup organs making them hard to kill. They also might use something different than normal neurons, which are not very fast, and indeed might need that to function since even the fastest neuron transmissions run at less than the speed of sound, millions of times slower than the speed of light. Or again, their brain may be distributed throughout their body. A caveat on the danger angle, besides intelligence, is just having vastly different biology. If they've got way faster reflexes because their body uses metal conductors for sending signals, then that critter might be able to react fast, and even might be able to have 100 limbs that it can control. Big might be very clumsy, but in a case like that, it might be able to circumvent the size issue with sinking into the ground by having 100 legs, and it might have tons of arms and fingers it could control with the speed and delicacy of a neurosurgeon. Critters like Godzilla are often implied to be using something other than flesh and bone for both protective hide and a power source, and we could imagine a creature with a natural nuclear reactor in its stomach or titanium and tungsten for scales. At that point, the dynamic changes, and it might be expelling superheated gas or combustible flames like a dragon, or shrugging off blasts from a tank gun. While fission reactors likely will occur naturally on younger planets with more uranium deposits, we think Earth had quite a few of them, and I could absolutely see an ecology spring up near these. I think it's a pretty heavy lift to imagine anything evolving this way, though. Of course, evolution isn't the only way to get to life, and the line between machine and biology can get rather blurry at higher technological levels. Outside of this case, though, you've got a real limit on your classic Godzilla-style kaiju walking around on 2 or 4 legs, and it's even tighter on anything wanting to fly around like a dragon, which would need wings hugely out of scale with its body even on a low-gravity planet. Now, something like the sandworms of Dune would tend to mass thousands of times what a dinosaur or whale does, in the high kilotons or even megaton range. But even a lack of feet in favor of a long, skinny body slithering around does have limits on what the ground can support. The cube-square law means if you double something's size, you raise its mass by 2 cubed or 8 times as much. And if you raise it by a factor of 1,000, you make it 1 billion times heavier. And that's the scale we'd be imagining with a sandworm when comparing it to a normal worm or snake. They still worked better on land than something with feet, though. The issue starts to be bones and foot and ankle size, because if I double your size, I need to more than double your foot, as it needs to carry 8 times the weight, whereas it would only have gotten 2 squared or 4 times larger, meaning you sink into the ground more. So even if we imagine an alternative chemistry for bones, something focused on iron or titanium instead of calcium, we still need to have much bigger feet if we're contemplating a walking skyscraper. Even using our biology though, you could probably get an organism a lot bigger than a dinosaur walking around. There are other problems like transporting oxygen around, or another fuel or nutrient. Even Scipion lungs for something more like collectors all over your skin, it takes a lot of internal plumbing and highways to move oxygen from the outside of some beast 100 feet wide to its insides. You need a lot more food too, though not necessarily proportional to your mass. As an example, smaller humans have a lot more surface area relative to their mass than bigger ones, and surface area controls heat loss, so a child uses most of their energy for staying warm. So a 5-year-old kid weighing 40 pounds might need 1,200 calories a day, while someone massing 400 pounds, weighing 10 times as much, might only need 3 times as much food. A big male African elephant might mass 70 times what a human does, but eat 35 times as many calories. things do not necessarily scale well, especially if we're moving into different biologies, such as a reptile, let alone an alien. A lot depends on your environment though, as colder water can leach heat off you pretty quick. A blue whale only masses 1,000 times what a human does and can eat 10,000 times as many calories as a human. Either way, it starts getting dubious if there's a size advantage for the purpose of obtaining food. Nonetheless, it is entirely plausible that a planet with lower gravity and higher biomass densities might see some titanic critters, but it would get dubious about them being more than an order of magnitude bigger even if they did use something stronger and lighter for bones. That dynamic changes a bit if we shift into something like the subsurface ocean of a moon like Europa, as even under a thick sheet of ice the water pressure isn't that high and doesn't rise as fast from the lower gravity. Organisms can adapt to very high pressure as we can see on Earth, but you do have some issues if your feet are getting much higher pressure than your head, and if you're 10 meters tall on Earth and in the water, your feet are indeed getting an entire atmosphere more pressure on them in the water than your head would be getting, and vice versa if you flipped over and dived. The biggest issue with subsurface oceans is that there isn't much sunlight coming in, and it makes it very dubious if any creature could be big and feed itself on whatever biomass was possible in the absence of marine snow from higher photosynthetic levels. Alternatively, on larger planets with sun and sky over the water, your pressure rise with depth from normal gravity would be rough on very large organisms. Our hydroshell artificial planet design does get around that. It tends to assume you have a layer of firmament in sphere form that's hollow inside, and you've dumped several planets with water on them, making for deep seas but very low pressure rise and probably a layer of transparent material on top. The assumption there is you might be providing lighting by vertical reefs, possibly big spiral mixers with lights on them that brought sunlight to lower levels and churned water and nutrients and air around. Very artificial planets, but the kind that allows some mega whale or kraken to exist. And if you're engineering anywhere, you might have living islands swimming around, underwater, or like the classic super big turtle we often see in stories where there's an island on their shell. We have the option for non-biological power sources at this point too, since we are talking engineered life on artificial planets. See our episode Oceans in Space, Marine Space Habitats and Preserves for more discussion of the hydroshell megastructure, its variants, and mundane and natural ocean planets. Our last major case is the idea that life might evolve on a gas giant. This seems more likely on other planets with big thick atmospheres such as we might see on mini-Neptunes, super-Earths or Hycean worlds. The classic image is the big gas bag or blimp creatures, and we could imagine things that looked like amoeba or a whale or a big squid that was basically tentacles coming down off a large balloon full of hot gas. Hycean planets get the name from shortening hydrogen and ocean, and are the idea that you might have a watery surface with a thick atmosphere that retained a lot of its hydrogen and helium from the higher gravity but still had oxygen and nitrogen and carbon dioxide. It would not be hard to imagine an organism developing to be able to separate out helium or hydrogen from that other gas and store it in a bladder as a lifting gas. Especially if it's a thick atmosphere which might limit light getting down to the water below, we could imagine big floating rafts of photosynthetic life adapting to float among the clouds on gas bags instead of on the sea. You might get some strange 3D ecologies floating around that atmosphere above the waves too, especially if it had some volcanic islands poking out. You might also get giant buoyant trees that have their surface on water, roots into water, and high trunks and branches with hydrogen or helium-filled balloons for leaves. It could probably deflate those to sink down into that protective sea at nighttime or the winter. The transition to get into space as a giant monster is harder here, and I'm not thinking a big gas bag is much of a threat, they would seem fragile. But speaking of transitioning to space, a good topic to close out on is asking what the Fermi Paradox tells us about giant space monsters. And interstellar migration is likely to be nigh impossible even for life adapted to live in asteroid belts. You are talking about needing either a natural nuclear reactor or the ability to survive without fuel in the dark interstellar void for tens of thousands of years to get to a new star system, which goes beyond hibernation for the season. So too, anything that big is likely to still be fairly uncommon and not have much biological imperative to get smarter to avoid predators, so a jump up to big civilizations and technology might be hard too. As a result, we can't look around at the universe as we see it now and say it lacks tons of giant space monsters, as they are likely to remain confined in the system they originate in, and so this may be common in the universe. They might also tend to prevent any smart and smaller civilizations arising if they are predatory and hungry. While I doubt they would be common, I think we have shown giant space monsters are possible today, and we might end up running into them frequently as we head out into the galaxy. They may even invite us to join them for dinner. And on that note, thanks for joining us for another Nebula exclusive.